Okay, so we're going to talk here about some of the physics underlying nuclear energy. Some points to make. First of all, nuclei are small, on the order of femtometers. A femtometer or a Fermi is about 10 to the minus 15 meters. For comparison, the size of an atom might be about 100 picometers, where a pico is 10 to the minus 12. And a nucleus might be on the order of 5 Fermis. So that's 5 times 10 to the minus 15 meters. So if we take the ratio of the size of the atom to the size of the nucleus, a typical value might be on the order of, this gives 20, this gives 1,000, I'd give about 20,000. So you can see that the atom is quite significantly large compared with the size of the nucleus. Now that's about the same as the ratio of size of, say, putting a ping pong ball at the center of a football stadium, because a football stadium might be about 500 meters. You know, the field is about 100 meters, but then you've got seating on either ends and structure outside, etc., etc. And a ping pong ball is probably about an inch or about 2.5 centimeters in diameter. And if you take the ratio of those two, it's also about 20,000. So that just gives you an idea of the scale. Okay, so there are typically several isotopes for each nucleus and element. So we represent these using nuclear notation. X is the name of the element. And then A is the atomic mass number. And then Z is the atomic number. So for instance, if we had this notation here, that's a Q, 9743. So we just look in the periodic table and we look for atomic number 43, and we see that's technetium. So this is going to be technetium 97. Likewise here, Pb is lead. It's got a mass of 210, but lead always has an atomic number of 82. So much so that we don't need to call this lead 82-210. We just call it lead 210 because the 82 is understood. So lead, we know, always has atomic number 82. So if we look at a couple of isotopes then, we've got lead 208. And because there's going to be 82 protons there will also be 82 electrons. And in terms of the mass, well, the protons and neutrons contribute to the mass because the electrons are a factor of 2,000 lighter than a proton. So we could see there's got to be 18, about 126 neutrons in that one. If we look at lead 207, well, it's still atomic number 82, so there's 82 protons and electrons, but there's going to be one less neutron. There's going to be 125 neutrons. Okay. Now, any sample of lead that you get is going to contain all of these isotopes. So, for instance, I think these numbers are accurate. You're going to have about 52%, which will be lead 208, about 20% that's lead 207, about 20% that's lead 206, and the remaining 8% is going to be lead 204. So if you work that out, that'll give you the average atomic mass for lead. That's why the periodic table doesn't have a round number. Well, there's another reason, but this is one of the main reasons why there's a leading decimal place in it. So if you work that out, we get 207.08. That will be the average atomic mass for lead. So our two messages so far are nuclei are small, and second of all, it's the message of isotopes, that an atom contains several different nuclei, which vary slightly in the number of neutrons. Now, in that list of isotopes, some of them are unstable, and they'll break up into smaller nuclei. These unstable ones, we call them radioactive. So, for instance, uranium-238, uranium has an atomic number of 92, it decays or breaks up into thorium-234. Now, in this decay, you don't lose particles. So if you had 92 protons there, you've got to have 92 protons on that side. That means we have 2 that are unaccounted for. So you don't lose charge. And likewise, you don't lose mass. So the protons and neutrons must still be there. So if there were 238 mass units on that side, there has to be 238 on this side, meaning there's 4 that was unaccounted for. So what is this particle? Well, this particle is called an alpha particle. Let me write the symbol alpha like that. And there's a number of other standard particles there, including the beta, proton, neutron, etc. So you should be able, using this chart, to balance a typical nuclear decay. So here's another example. So we've got nitrogen-14. Now, that's an isotope of nitrogen with a mass of 14. Nitrogen always has atomic number 7. It absorbs an alpha particle. So an alpha particle collides with it. Alpha particle is mass of 4, charge of 2. It's the same as a helium nucleus. We're then told that this decays into oxygen-17. So 17 is the mass number. Oxygen from the periodic table always has an atomic number of 8. Then there's got to be some other particle here. 14 and 4 gives 18 units of mass on that side, so there's got to be another unit here to balance that. 7 plus 2 is 9 units of charge, so there's got to be another 1 unit together with the 8 to balance. So 1, 1 is a neutron. Or sorry, 1, 1 is a proton. Mass of 1, charge of 1. So there's a proton emitted in this nuclear decay. Our next message is these decay products tend to be moving quite quickly, and as a result, we can do a number of things with them. We can harness that energy for for making bombs. We can harness that energy for making electricity. We can harness that energy for various medical treatments. But if we're not careful, that energy can also be dangerous. So when you've got this highly energetic alpha particle passing through your body, it can cause what's known as ionization damage. And what that refers to is when, let's say, this little alpha particle, which is, of course, microscopic, right? It's even, it's the size of a helium nucleus. So we've seen nuclei are on the order of Fermis, 10 to the minus 15 meters. If that passes, encounters your skin, then what's going to happen is, if we were to look with subatomic eyes, we would see that a whole bunch of negative charges have gotten ripped off of the atoms. And so we've created what's known as ionization damage in that little bit of skin where this alpha particle was targeting. Now, that ionization that you get there, and this is, say, on the surface of the skin, inside the skin cells, it can rip apart cells. It can damage macromolecules inside the cells, damage the chromosomes inside the cells. It can kill the cells. And if you happen to be getting that down here in your gametes, then the damage that the ionization causes can actually lead to birth defects. So that tends to be why these things are dangerous, because as they hit our skin, or as they pass through us, which gamma rays do, they create ionization. They rip electrons away from the atoms. And those charges then are very reactive. They're very short-lived reactive chemical intermediates, and they could cause a lot of damage to the cellular processes in the cell. Now, we can use ionization to detect radioactive particles too, because if you have a detector here, if a radioactive particle happens to zip through this detector, then it'll create some ionization here in this low pressure gas. Now, the way the detector works is the housing would typically be, say, grounded, and then there'll be a high voltage wire here, and then this ionization in the gas will enable a current to flow. So there would be a current flow from the high voltage wire to the grounded housing. And when there's a pulse of current that flows, we can detect that and we can count the number of times that happens. So particle passes through the chamber, creates ionization. That ionization allows this gas to conduct electricity, and when it conducts, you count. That's the basics of a Geiger counter. And that's what's summarized for you right there. So there's no doubt that there is a risk to radioactivity because that ionization damage can be significant. If you get enough particles passing through your body, they actually deposit a lot of thermal energy, and you get burns. And those tend to be the most serious cases. And typically, if you're getting radiation burns, that means you've probably had a fatal dose of radiation, and unfortunately, it will not last very long. Now, the danger posed by radioactivity is related to several things. First of all, it depends on, well, which particle you're talking about. Because gamma particles, which have no mass and no charge, they tend to pass through tissues. And gamma particles are, say, very high energy X-rays. So they'll get absorbed by bones, but they tend to pass through tissues fairly easily. Alpha particles, because they're got both mass and charge, significant mass and charge, they tend to do a lot of ionization damage. So they are a lot more worrisome than either gammas or beta particles. So it depends on what the particle is. It also depends on where in the body you're being exposed. So being exposed in your gonads is obviously more serious than just getting a small dose on your skin. Then it depends on how many radioactive nuclei you've been exposed to. And the key variable there is the activity rate, which depends on, or rather is related to, the number of decays each second. So the activity rate can be measured in a couple of units. One of them is becquerels, that's a decay per second, and then a curie is 37 billion becquerels, 37 billion decays per second. Now there's a relationship between the size of the sample and its activity, okay? And they're related through something known as the decay probability constant. This is just the number of decays you get per second per atom. So it's really just the odds in a given second, or rather in a second, that an average atom would decay. So the probability then of a decay happening multiplied by the number of atoms present, that's going to give you the number of decays per second. And we'll introduce the variable r there to measure the rate, the activity in decays per second. So this equation then governs radioactive decay. Now, just looking for something here. Okay, things are a little bit out of order there, but here it is now. But that rate, of course, is the number of decays, which is the change in the number of radioactive particles per second. So we've just showed that the rate of decay, r, which is the probability times the number of particles, is directly related to how quickly the number of particles is changing. Now, in science, this is an example of, and math as well, I suppose, this is an example of what is known as a differential equation. And it's a really important one because it appears everywhere in science. When you've got the rate of change of a quantity that depends on how much is there. So this sort of equation applies to population as well. And it also applies to radioactive decay. So this differential equation has a standard solution, and this solution involves an exponential function. So the number of particles at any given time ends up depending on the number that you started with times a decaying exponent of time with that probability constant. So this just says that if you start with a certain number of particles, the number is going to drop like an exponential decay function. So here's an example. So here we've got a sample with this decay constant, 0.012 decays per second per atom, and then we've got 0.05 grams of the material. And we just want to find out something about the number of particles versus time. So first of all, we have 0.05 grams of the material. But then we know that a mole, or rather we're given that a mole is 420 grams. So that converts to moles. Then we'll just convert to particles using Avogadro's number, 6.02 times 10 to the 23rd. This is the number of particles in a mole. So this gives us 7.17 times 10 to the 19 radioactive particles present initially. Okay, now the initial decay rate. Well, the decay rate is proportional to, so this is the initial number. Let's introduce a symbol for part A. This is the initial number of particles present. So the decay rate is the product of the number of particles you have times the chances of them decaying. So there's 0.012 decays per particle per second, or really just reciprocal seconds. And then you've got 7.17 times 10 to the 19 particles. So because you've got, a reasonably large number of particles, 1/10,000th of a mole of particles, you are going to see a fair number of decays each second. So 8.6 times 10 to the 17 decays each second. So if we wanted to describe the number of particles as a function of time, we know that it's a decaying exponential function. And the initial number that we have is this 7.17 times 10 to the 19. And we've got a decaying exponential with this as the lambda constant, 0.012 t. And because this is in units of seconds, or rather this is reciprocal seconds, we have to put time in seconds. So for instance, to find the number of nuclei present after 200 seconds, you just put in 200 for time. So you got to do 200 times 0.012 negative, and then do the e to the x function, and then multiply by 7.17 times 10 to the 19. When I do that, I get 6.5 times 10 to the 18 particles left. So it's gone down by a factor of about 10. Now, how long would it take for the number of particles to drop considerably by a factor of about 10 to the 6? So in that case, we know the number of particles, and we want to find the time. So you just put the number of particles in for n. And I'm just going to leave lambda as lambda for now. So this is e to the minus lambda t, and you want to solve for t. So you're going to divide both sides by this number. And I got badly mixed up there when I was writing that, so let's fix that now. Because, of course, it was 7.17 times 10 to the positive 19. Okay, so dividing this is going to give you e to the minus lambda t. Now, if you want to solve for t, the next thing you have to do is do the natural log of both sides, because when you do the natural log of this thing, it'll equal the natural log of e to the minus lambda t, but natural log is an inverse function of e, so this just gives minus lambda t. So then you can solve for time. It'll be minus 1 over lambda times the ln of this ratio, which now I'll write in. 6 times 10 to the 13 divided by 7.17 times 10 to the 19. And this will give you a time in seconds, because this is in units of seconds. And if you convert that, it's quite a few seconds, but if you convert it, I get 1166 years. So it's going to take about 1,200 years for that number of particles to decay by a factor of about by about 6 powers of 10. All right, so exponential decay is a really important concept in nuclear physics. The number of nuclei that you have is going to decay exponentially over time. Now, another really important concept is the concept of half-life. Because the half-life tells you if you start with 100 nuclei, and if you have a half-life of 100 seconds, then each 100 seconds, that 100 that you started with is going to drop by a half. So you'll only have 50 left after 100 seconds. Then you'll only have 25 left. Then on average, you'll only have 12 and a half left after 3 half-lives. So although it hasn't completely decayed in 1 half-life, that gives you at least a measure of time that tells you how long you should be worried about the radioactivity. For instance, cesium-137 has a half-life of hundreds of years, so you know that those radioactive particles are going to be around for a long time. Radioactive iodine, on the other hand, just has a half-life of a few weeks, so it's going to disappear much more quickly. Now, if we look at our equation for the exponential decay of radioactive particles, if we have a half-life gone by, that means that half the nuclei are going to disappear. So this is just half of what it was before, i.e. it's n naught over 2. So we can cancel the n naught and just say 1/2 is e to the minus lambda t. Then we're just going to do the natural logarithm of both sides. Now when I do the ln of this side, I'm going to get minus lambda t. Then I'm going to divide both sides by minus lambda. So I'm going to get ln of a half with the minus and then a lambda. According to the log property, this minus can get brought up here as an exponent, and then a half to the minus 1 is just 2. So minus ln of a half, according to the log properties, is the same as ln of 2 over lambda. Now this time is the half-life time, and we tend to give it a special symbol. It's t 1/2. So now we see that the decay probability constant is related to the half-life of a material. So for instance, if you had a half-life of 9 months for this mated upium, then you can find the probability decay constant, because that's just ln of 2 over the half-life. Now, to work in seconds, in months, for time in months, it's just 9 months, right? And this is going to have units of 1 over month. But if you want to work in seconds for your time, then you need an assumption about how long a month is. Probably it's 30 days. And then each day has 86,400 seconds. So this would be the decay probability constant in reciprocal seconds. All right, so The rate at which decays happen is an important thing to know about in terms of evaluating the safety. And we saw that the rate at which radioactive particles emit radiation is a decaying exponential function. So we can quantify the dangers of radioactivity, and we can measure it. When we get around to talking about the effect on the human body, there's a couple of variables that we use. The first is the dose. That's just the amount of energy that gets deposited in your tissues by the ionizing radiation passing through it. So the units are a gray, and a gray is just a joule of energy deposited in a kilogram of tissue. Now, this doesn't distinguish between the different types of radiation and the different types of tissues. The variable known as the effective dose does distinguish between those two. Now, dimensionally, it's going to be in joules per kilogram, because you just take the dose and multiply by a couple of weighting factors. But to note that, or to represent the fact that this is now taking into account both the type of radiation and the tissue that's hitting, a new unit is introduced, and that unit is a sievert. So a sievert's equivalent to a joule per kilogram, but as a joule per kilogram, it takes into account the type of the particle, something known as the weighting factor, and the damage that it does, and also the type of tissue that's being hit and how readily it's damaged by radiation. So alpha particles tend to do a lot more damage, so roughly a weight of 20 times more biological impact for a given dose of alpha particles as compared with gamma and beta. So this is the particle weighting factor, WF. Next, the tissue weighting factor. For a given dose, there's a lot less effect if it's, say, the skin being irradiated than if it was, say, the bone marrow or the colon. Both of those are very sensitive to radiation. And so putting that in, the tissue weighting factor, along with the radiation weighting factor, the nature of the particles, multiplying by the joules per kilogram, that gives you the idea of the biological impact. Now, that's in sieverts. What sort of doses do we have to worry about? Well, if you get a sievert of effective dose, that's a big dose, and there will be some signs of radiation sickness there, and there will be an increased risk of cancer of about 5% from that dose. Now that was a full sievert. The annual limit for radiation workers is about 500 millisieverts. In the recent Japanese accident, I believe some workers were exposed to up to 250, but they then basically have to retire and they can't work in the industry anymore. So that 250 millisieverts is a quarter of a sievert. So they just got an increased cancer risk of a quarter of 5%. So their cancer risk went up at about 1% higher than the average population, but they probably saved the accident from being a lot worse than it was. So, they're heroes in a way because they have a 1% increased risk of cancer, but they made things a lot better for the Japanese population. Anyway, so let's say a radiation worker received a dose of 50 millisieverts, and that is the annual limit for them. And we just want to say, okay, if that was exposures to gamma rays in the bone marrow, what was the actual dose in joules per kilogram? So the relationship here, remember, is that the effective dose is the dose, which is the energy deposited in the tissue, times a weighting factor for the type of particle and for the type of tissue that was radiated. So these are gamma rays, so they have a weighting factor of just 1. We were hitting the bone marrow, which is the most sensitive tissue, along with the colon. And we had about 50 millisieverts here, 50 times 10 to the minus 3 sieverts. And then what was the dose? Well, dividing by 0.12, you get a dose of 0.417. And now we'll put in the proper units for dose. That's in grays or joules per kilogram. So this worker, over the course of a year, the total dose was a total energy of 0.4 joules of energy deposited per kilogram of tissue. Now, there's something known as the linear dose-response model. That just says that every sievert that you get, every increased sievert increases your risk. And we can just use proportionality. Every sievert that you get increases your cancer risk by 5%. So this 50 millisieverts, how much did it increase your risk by? Well, it's going to be 5% times 50 times 10 to the minus 3 over 1. And that works out to 0.25%. So in a population where the incidence of cancer is about 50%, your chances just went from 50% to 50.25%. It's not a huge increase. If you have, say 100 people, that would mean there'd be an extra 0.25 cases. But if you had 1,000, if you had 10,000 people, that would mean there'd be an extra 25 cases of cancer. So it is significant. It's definitely measurable. But the point is that it can be quantified, and we can evaluate the risks of doing this with other risks, because there's no such thing as no risk, especially for an energy source. And nuclear power, while it has its risks, is not alone in that. And, lots of people are probably experiencing lung conditions because of breathing coal pollutants. Certainly in very industrialized regions of China, that's the case. All right, so now, in nuclear power, we are harvesting those highly energetic decay particles, the alpha, betas, and gammas, that are coming from the nuclear decay of the radioactive isotopes. But why is there so much energy involved? Why is it that uranium has this tremendously huge energy density? Why is, the radiation from these processes so much more dangerous than, any sort of chemical reaction that you might encounter in the lab? Well, it has to do with the fact that the nucleus has a tremendous amount of energy in it, and the reason it does is it must be held together. And the nucleus is held together by a bunch of positive protons. Sorry, the nucleus contains a bunch of positive protons which repel each other really highly. There's a big electrostatic force there. So there must be something else that's holding them together, a really, really, really strong force to overcome that force of positive repulsion, positive repelling positive. So there is a strong force there. It's called the nuclear strong force. And there is a related energy known as the nuclear binding energy. Now, this tends to be quite large, and we can see evidence of that nuclear binding energy in what's known as the mass deficit. The mass deficit is just the difference in mass between the separate constituent particles that make up an atom or nucleus and the actual nucleus. If there's a tiny little bit of mass deficit, then according to the Einstein principle, there will be a corresponding amount of energy. Now, because that little mass deficit gets multiplied by the square of the speed of the light, which is almost 3 times 10 to the 8, a little bit of mass will give you quite a bit of energy. Here's a diagram showing energy versus separation distance. So this is all the separate particles up here. So, for instance, in the case of helium, this would be, a proton, and a couple of neutrons. So that's the particles just separately by themselves. When they bond together, they actually have a little bit less mass and a little bit less energy. And that little bit less mass and energy is related to the stability of the nucleus. Okay? The bigger the difference between the separate particles and the bound particles, the bigger the difference, the deeper this well is going to be, and therefore the more stable the nucleus is. So, the mass deficit is just the difference between the separate particles and the bound particles. It's related to stability. Now let's just do a few calculations here. Let's take an atomic mass unit, which is this many kilograms, and convert it to energy. So let's say we had a mass deficit of 1 atomic mass unit. Well, according to the Einstein equation, we can convert from a mass deficit to an energy using this relationship. So for the mass deficit, we put in 1.660539 times 10 to the minus 27 kilograms. And then we put in the speed of light, and that's 2.9979 times 10 to the 8 meters per second squared. Now you may be wondering why we're keeping all these significant digits. It just turns out that there's a value here that we want to know fairly precisely. Okay, so when we work this out, we get 1.492 times 10 to the minus 10. And then the units here are kilograms meters squared per second squared. That's a unit of joules. Now we want to convert that to a different unit that's useful in atomic physics. We defined a voltage as an energy per charge a few classes ago. So we see that an energy is a charge times a voltage. Now, if we express the charge in terms of the number of fundamental charges, little e, where little e is the charge on an electron, and then the voltage is just a voltage V, you could see that an eV, or an electron volt, is a unit of energy. Now, because this fundamental charge is 1.6 times 10 to the minus 19, an eV is 1.6 times 10 to the minus 19 joules. So if we go back to that number that we had on the previous page, the 1.492 times 10 to the minus 10 joules, and we convert it to this atomic energy unit, and this is kind of one of the steps in physics where you can talk like a physicist. You learn to start talking in EVs instead of joules. Then we want to cancel joules, replace with EVs. 1 EV is this 1.602176 times 10 to the minus 19. Now, if you work this out, it's 9.31 times 10 to the 8 EVs, or 931, and then this will be 10 to the 6, and 10 to the 6 is mega EVs. So an atomic mass unit, when you convert it to energy, is 931 MeVs. And in particle physics, they're always talking about MeVs and GeVs and TeVs of energy. All right, so why is that important? Well, this is 1 AMU is equivalent to that much energy. So let's go back to the atom, the nucleus, and try and calculate some binding energies. Because that's the energy that's going to get released when we have nuclear decays, and we're going to use that to make electricity. So here it is right here. If you keep a few more decimal places, an atomic mass unit's 931 MeVs of energy. Here's the proton, neutron, and electron measured very carefully in terms of AMUs. Let's calculate a binding energy of a simple nucleus. Let's go for an isotope of hydrogen called deuterium. Now then, it's got an atomic number of 1, so there's 1 proton there. It's got a mass number of 2, so it's also got a neutron. And then the number of protons equals the number of electrons. So if you look back on that previous page, a proton is 1.007276 AMUs. And then the neutron, a little bit more, 1.008. Oh, I have to look back. Oh, no, it is on the page, right down there. Where was it? Come on, you. Here. Yeah, it's down here. 1.00866 AMUs is the neutron. And then the electron, much smaller than the 2, is 0.00054 3.86 AMUs. So if you add up all of those separate particles that go into making a deuterium atom, you get a total of a little bit more than 2 AMUs, 2.016, then it's 4896. So that's the total of the separate particles. But if you take an atom of deuterium and you actually measure it, you get less than that. You get 2.014102. Why isn't it the same? Well, remember, some of this mass, okay, is being converted to energy, and it's that energy that's holding the nucleus together. How much is it? Okay, well, the constituent particles, we said, was the 2.164896, and then the actual deuterium, when you get them all together, is less, 2.014102, and that is the mass deficit. And of course, we multiply that mass deficit by the speed of light constant. Or we can use this ratio that we previously derived, because you see this is the mass deficit. And how much is it? It is 0.0023876 in units of AMUs. I can use the work that I did in the previous page. When I know the mass deficit in AMUs, I can just multiply by this ratio. So the amount of binding energy, the energy that's holding the deuterium nucleus together, that could be potentially released in a nuclear reaction, is going to be this 0.0023876 AMUs multiplied by 931.494 MeVs of energy for every single AMU that's converted to energy. Now, we're not converting very many AMUs there, so the binding energy of deuterium, if you multiply the 0.02387 by 931.494, you get 2.2 MeVs of binding energy. So that's the energy holding a single atom, a single nucleus, in fact, of deuterium together. Here's one for you to try, carbon-13. So think for a moment about what's in it. Add up the mass of the separate particles. Here is the mass of the actual nucleus. It'll be this different from the constituent particles. Find the mass deficit in AMUs, convert it to energy in MeVs. Pause the video, give it a try. Then you can turn it back on and watch it if you want to check your work. Okay, so hopefully you had a chance to give this a try. Carbon-13, carbon has an atomic number of 6, so there's 6 protons, 6 electrons, and because it's a mass of 13, there'll be 7 neutrons. So you multiply this by the 1.07276, the electrons are the 0.0005486, and the 7 neutrons are the 1.08665. That gives a total of 13.003355. Again, that's in AMUs, and again, that's different from the actual atom. So there's a mass deficit. Subtract this from this, and it is 0.104 AMUs of mass difference. For the binding energy, it's the mass difference converted to energy. Now you can, if you want, change this back to kilograms and multiply it by 3 times 10 to the 8, or you can just use the fact that we've already done that work and we know the AMU equivalent of energy. It's 931.494 MeVs of energy for single AMU. And so the amount of energy that's holding the carbon-13 nucleus together is 97.11 MeVs. You'd have to do that much work, provide that much energy to separate the nucleus. All right, so what does this have to do with nuclear energy? Well, here's the deal. In a nuclear decay reaction, you're dealing with an unstable isotope that's decaying and forming more stable daughter particles. So that means that at the beginning, what you started with was not as deep a well because it was unstable. What you end up with is a more stable particle, a deeper well. That means there's an energy difference there, okay? And because this is a well, because you're going from a less deep well to a more deep well, there's energy released. So the amount of energy that's released in a nuclear reaction is the difference in the binding energies. And if you're going from something like uranium, which is quite unstable, to some more stable particles, that difference in binding energies can be really significant. It's worked out in the textbook, and we show there that every uranium nucleus that fissions produces about 200 MeVs of energy per each decay. So let's say in a reactor you had 202.7 kilocuries. Now, that's 202.7, and a curie, remember, or you could look back, is 37 billion decays every second. Okay, so, multiplying those together, there's something like 10 to the 15 decays going on there. So that's the number of decays each second. Now, each one of them produces 200 MeVs. Now, it's useful in atomic terms to talk about MeVs, but if you look at what we're doing here, we're going from the microscopic problem of a single decay, and suddenly we're talking about our heat exchanger and the power produced. In order to answer that question, we don't want in MeVs, we actually want this back in joule units. So mega is 10 to the 6. So there's 10 to the 6 in a mega. And then an electron volt, we can look back and see that that's 1.6 times 10 to the minus 19 joules. That's 10 to the minus 19 joules there. Let's clean that up. And so we can now see, based on the decay rate in our uranium reactor, so this is just the counted rate. There's like 8 times 10 to the 15 decays each second. We can see how much energy we're making. Now, that is going to be thermal energy. And then we managed to capture 38% of that and use it to boil water and transfer that energy to the generator. The generator, which converts the steam pressure to electricity, is remarkably efficient, about 85% of that. So all of these numbers here, we're going to multiply by 38%, because that's the amount of thermal energy from the nuclear decay that we managed to capture. And then about 85% of that thermal energy will get, of that steam energy will get converted to electricity. And that works out to 77,519 joules per second. This is a 77.5 kilowatt generator. That's not a particularly large nuclear cell, but it just, again, sort of shows you the key variables. So our message about nuclear energy is the nuclei are small, there's isotopes that are unstable in decay, the decay particles are moving quickly, they can cause ionization damage in tissues, or we can capture the energy of those particles and use it to boil water. The energy in those particles is really large because we're dealing with the binding energy, the energy holding the nucleus together, and the particles in the nucleus are highly repelling, so binding energies are really significant. Lastly but not least, we can quantify the risks of nuclear energy using doses that we can measure and also things like activity rate that enable us to know how long a sample is going to be dangerous. This is the basic physics related to nuclear power.